Welcome back. This is the last portion of our introductory mini unit. This is primarily a review of stoichiometry. We're going to look at how to perform stoichiometry calculations. So this is a Regent style question. How many moles, given this balanced equation, how many moles of oxygen are needed to produce 8 moles of water? When you're setting these up, do them as a factor label problem. You want your number, your unit, and your substance. We use the coefficients in the balanced equation to help us out here. So we're looking to get to moles of oxygen. So we want to put 1 mole of oxygen on top because that's the coefficient of the oxygen in the equation. 2 moles of water on the bottom. So our units cancel. So our answer is 4 moles of oxygen. For a simple problem like this, which is not something you'd be likely to see on a AP test, you can set it up as a proportion if you'd like, but always show your work. So as a review for chemical equations, the chemical change involves a reorganization of atoms in one or more substances. You have parts of an equation, you have your reactants and your products. Anytime you have a balanced equation, the coefficients in the equation correspond to the number of moles of each substance that you're working with. When you're dealing with multi-step stoichiometry problems, you want to make sure the equation is balanced. On AP questions, they will give you the balanced equation, so you're not going to have to do that and then work with it, because if you mess up the balancing, you're kind of snowballing. You want to make sure you always get to moles. If you don't start with moles, you want to get there. It's the easiest thing because then you can convert into anything else. You have to work with your coefficients. That's where these mole ratios come into play. That will switch your substance from one to the other. And then get to whatever unit that you need that the question is asking you for. You have to make sure you get to moles. So here's a quick example. 6.5 grams of aluminum reacts with an excess of oxygen. How many grams of aluminum oxide are formed? So we have our balanced equation. We have our reactants, and we have our product. And our coefficients are always going to be those smallest whole number coefficients for the equation. Make sure you do that. Most questions will say that. Smallest whole number ratio. So for this problem, the way you would set it up using factor labeling, you always write down what you're given first. So we're given 6.5 grams of aluminum. That's what we write down first. We know where we're going. It's telling us you want to go to grams of aluminum oxide. So you have that as your target. When you start with grams of aluminum, I can't do anything there. I have to get it to moles first. So that's using the gram formula after the atomic mass of the aluminum. Our next step is to get rid of the aluminum by setting up the coefficient ratio and get to the substance that we want. And then, since this question is asking us for grams of aluminum oxide, you would use the gram formula mass, in which the units are grams per moles there, and then just calculate. In a lot of cases, you'll be working with limiting reactant problems. So in a limiting reactant problem, you'd be given a starting quantity of each of the reactants in the reaction. One of them is going to run out first and limit the amount of product you can make. This was like the last part of the summer assignment. So something's going to run out, and some parts will be left over. So checking this one out, we have high synthesis of water. This reaction, properly done, produces energy in the form of electricity and water. In the form of electricity and water. Suppose a fuel cell is set up with 150 grams of hydrogen gas and 1,500 grams of oxygen gas. How many grams of water can be formed? So for this equation, or for this calculation, you're setting up 2 stoichiometry problems. One of your calculations is going to start with 150 grams of hydrogen gas, and the other is going to start with 1,500 grams of oxygen gas. Both of them are going to terminate with grams of water, because that's what you want to compare, is how many grams of water you're able to make. So for the hydrogen and the oxygen, we'll have 2 different setups. You always want to write down number, unit, and substance. If you do not label your calculations, I cannot grade your calculations. The readers cannot grade your calculations. Convert to moles. So now we've gotten rid of grams of hydrogen, we have moles. The next thing is take it to water. How can I take moles of hydrogen into water? I would convert to moles of water using the coefficients from the equation. So mathematically, this step, H2O, isn't going to do anything, right? The 2's will cancel out, but it gets us the unit that we want. And now we want to get to water. So 18.016 grams of water per mole. So that is the gram formula mass of the water. We'll do the same setup for the oxygen. Take it to grams of water. And we plug our numbers in. So 150 divided by 2.016 times 2 over 2 times 18.016. And that gets us 1340.47619 grams of water, which we don't have to worry about sig figs yet. 1500 divided by 32 times 2 times 18.016. And that is 1689 grams of water, exactly. Okay, so looking at this answer, that tells us that because the hydrogen that I have available to me produces less water than the oxygen that I had available to me, it tells me that the hydrogen is going to run out first. So the hydrogen is my limiting reactant. How many grams of water can be formed? Well, this much water. Now, if we went around this using sig figs, 150 grams has 2 sig figs. This has 4. Mole ratios don't factor into sig figs because those are exact values. And this one has 5 sig figs. So your answer would get cut down to 2 sig figs. So you could round this to 1,300 grams of water. And those are your 2 significant figures. Adipic acid is used to produce nylon. It's made commercially by this controlled reaction between cyclohexane and oxygen. Assume you carry out the reaction with 25 grams of cyclohexane, and that's the limiting reactant. So the cyclohexane is going to run out first. We have plenty of oxygen available. What's the theoretical yield of adipic acid? So 25 grams of cyclohexane. Again, you don't have to know that's the formula for cyclohexane. They'll tell you in the problem. Like, oh, well, they didn't tell you what cyclohexane was, but you know what oxygen is, so you obviously know the other one. Okay, oops, times 6. And, okay, so we want to figure out the theoretical yield of adipic acid. So we can convert this to stop at moles if it doesn't specify. So usually it'll specify. Let's take it to grams. So I think that'll lead us into the next problem. So convert this to moles first. Gram formula mass. Mole ratios. So get rid of the C6H12 and get to adipic acid, which is 2 moles. I'm just writing ADP because I don't feel like writing the whole thing out. And now we can convert that to grams. 1 mole of adipic acid. And we have, I should have done this ahead of time, sorry. 6 times 12.01 plus 64. Okay, so I got 146.14 for the gram formula mass. So now I plug in 5 divided by times 2 over 2 times 146.14, and that gets me 43.4 grams of adipic acid. And I did 3 sig figs because of this starting value having 3 sig figs. So 43.4. So that's theoretically, the theoretical yield is what your math predicts that you should get. Okay, so now this is saying for part B, if you had obtained 33.5 grams of it, what's the percent yield? So it's kind of like percent error. Percent yield is what you got divided by what you should have gotten based on your mathematical prediction times 100. So 33.5 divided by 43.4 times 100. This is not a calculation that's on your reference sheet. But think of it as a comparison. What did you get compared to what you should have gotten times 100? So that is your percent yield. It is possible to have over 100% yield. Let's say some other, like something was contaminated with excess adipic acid or excess cyclohexane was there. You didn't measure your cyclohexane correctly at the beginning. That could cause your yield to be over 100%, but it doesn't happen very often, especially in a controlled setting. So this problem, what mass of P4 is needed to produce 85 grams of PF3 if the reaction has a 64.9% yield? So they're telling you the percentage, 64.9 equals what mass is needed to produce 85 grams of PF3. So you have to work and calculate using the 85 grams of PF3, take it to grams of P4, and then knowing that the reaction only has a 64.9% yield, you could figure out what mass you'd actually need to put in to get there. It has to be higher than it has to go over what you should get. So this we'll take a look at in a little more detail in class, but you're going to be working on some limiting reagent problems together, as well as some particle diagrams where you can look at how the particles react with one another. The end.